Welcome back. Let's now introduce the principle of inclusion-exclusion. So previously we had the addition principle, and that was specifically talking about an event where we were interested in counting up the probabilities of the outcomes inside that event. The inclusion-exclusion principle, this is what if we're talking about two events and we wanted one event or the other or both to occur. Good news is that the formula for inclusion-exclusion is very similar to the counting one that we had. If you're referring back to chapter 3, the counting version for inclusion-exclusion was almost identical. It's just instead of being probabilities, it was numbers of things. So it was the number of things in E union F would be the number of things in E plus the number of things in F minus the number of things in E and F. Here it's exactly the same, except the formula has just been changed to be probabilities of. So pretty much same formula as before. And same as before as well, if you have two things that don't overlap, if E and F are mutually exclusive, then E intersect F would have a probability of 0, so there would be nothing to subtract. So we have kind of a special case here for the inclusion-exclusion principle. What if it's E and F that are disjoint? Well, if you're looking for E or F to occur, it's just the probabilities for E plus the probabilities for F added together. Okay, let's use this inclusion-exclusion principle for the following. We are interested in drawing a card from a standard deck. So again, we are selecting one card at random. We know then it's a uniform sample space, 52 things inside of it. And what we're interested in is the probability of getting, for the first one, an ace or a 2. So probability of ace union 2. First off, I'm going to think about, are these events mutually exclusive? Are they disjoint? If you get an ace, could you also be a 2 at the same time? And the answer is definitely no. If one is happening, then the other is not happening. If the card is an ace, it's definitely not a 2. And if it's 2, it's definitely not an ace. So this is mutually exclusive. We just need to add what's the probability of getting an ace plus the probability of getting a 2. And for the aces, there's 4 out of 52 in the deck. And for twos, there's 4 out of 52 in the deck. That adds up to 8 out of 52, or 2/13. Okay, let's carry on. Ace or a red card. So for this one, I have to again think about, is this something where there's an intersection? So is it possible for you to be an ace and also red at the same time? And the answer is definitely yes. You could be an ace and also red if you were the ace of hearts or the ace of diamonds. So I need to use inclusion-exclusion with the first version where there's subtraction. I'll need to find the probability of an ace plus the probability of selecting a red card, and then minus the probability of selecting the overlap, minus the probability of selecting a card that is red and an ace. Okay, so now let's do. Starting with aces, there are 4 aces in our deck, 4 out of 52. And then as far as the red cards go, half of the cards are red, so that's 26 cards that are red out of 52. And then finally, we need to subtract the overlap because there are some aces which are also red. And I said before, that's the ace of diamonds and the ace of hearts. There's 2 cards out of 52 where that's the case. So I have 4 out of 52, probability of ace, plus 26 out of 52, that's probability of getting a red card, and then minus 2 out of 52, that's probability of getting a card that's an ace or red, and this all adds up to 7/13. Okay, last part, the probability of getting a diamond or a face card. So same thing as before, I ask myself, is it possible for these to overlap? Could you be a diamond and also a face card? Yes, you definitely could. If you were the Jack of Diamonds, Queen of Diamonds, or King of Diamonds, you would be in both of those events. So I will need to use the first version of the formula that has the subtraction. I'll find the probability of selecting a diamond, and then I'll add on to it this probability of selecting a face card, and then subtract the probability of the overlap. Probability of getting a diamond, that's also a face card. So starting off with diamonds, in our deck, there are 13 cards for each suit. So there's 13 out of 52 cards which are diamonds. And then adding on to that, the face cards. So we know jacks, queens, and kings, those are the face cards, and there's 4 of each. 4 jacks, 4 queens, 4 kings, that's 12 out of 52 for face cards. And then finally, subtracting the face cards which are diamonds and also subtracting the cards which are diamonds and also face cards. So diamond and also a face card, that would be the Jack of Diamonds, Queen of Diamonds, King of Diamonds. There are 3 out of 52. And so then only thing left for us to do is then compute 13 out of 52 plus 12 out of 52 and then minus 3 out of 52, which gives me 11 out of 26. All right, let's do another example. So here I've got a sample of 100 people, 46 speaking French, 74 speaking English, 28 speaking both. Randomly select one person. What's the probability that the person speaks French but does not speak English? So this is another sort of a moment where maybe we might be interested in using one of our previous techniques. I'm thinking in particular about using a Venn diagram. The reason I'm thinking about this is because I have 2 events that I'm thinking about. I have people who speak French. I have another event, people who speak English. There'll be an overlap. There'll be the people who speak both of them. Now, what I could do if I felt like it would be to define 2 events. I'll have let E be the event that the person speaks English. And I'm going to have F be the event that the person speaks French. And I could fill in a Venn diagram, and I could fill it in, but what I'm going to do is instead of filling it in with numbers of people who speak French or speak English or speak both, I'm going to fill things in with probabilities. I'm just going to make some notes here. If we have 100 people and 46 speak French, then the probability that F happens, that I select a person and they speak French from this group, is 46 out of 100, which is 0.46. And I could also say the probability for English being the outcome is 74 out of 100, 0.74. And then finally, we have 28 who speak both languages. So that's people who speak English and also French. That's 28 out of 100, or 0.28. So what I'm going to do now is I'm going to draw myself a little Venn diagram, and I'm going to put in the probabilities just in the same way that we did back in chapter 3. We're starting in the center and then working my way outside. So to begin with, in the center, E intersect F, 0.28. That's the probability of being in that overlap. Now, we know in the English circle, probability of being in that circle is 0.74, the 74% chance of speaking English. We already have some people in that circle. We've already put in 0.28. So the same as before, we're going to use subtraction to figure out what's in the remaining zones. So 0.74, all of E should add up to that. I've already put in 0.28. So 0.74 minus 0.28 is 0.46. Similarly, I have in the French circle that this should all add up to 0.46, and I've already got 0.28 in it. So 0.46 minus 0.28 or in other words 0.18, that should be the probability of being in just inside of F. And just to finish this off completely, remember that everything in our sample space, all of our probabilities should all add up to 1. So that means the exterior plus these three numbers should all add up to 1. Currently in my Venn diagram, I have 0.46 and a 0.28 and a 0.18. Currently in my Venn diagram, I already have this adding up to 0.92. So if I need everything to add up to 1, then 1 minus 0.92, 0.08, that should be the exterior. I probably did more work than we needed to do because we could have answered the question a while ago. The question is, what's the probability that this person speaks French but does not speak English? So the real question we're interested in, what's the probability of being inside of F and being not inside of E? So being inside of F and not inside of E, those are the 18%. That's the 18% who only speak French. It's good, though, to think about the other things that we could get out of this. So we know that there's 8% who don't speak French and also don't speak English. There's 28% who speak both. There's 46% who are English only, with a Venn diagram that gives me, just as it did before, even more information than the inclusion-exclusion principal formula does. Okay, let's do another example. We've got three events here, or an A, a B, and an A intersect B, where we've got values given to us. For part A, all I'm interested in is finding the probability of A union B. And so for that, I could just use the inclusion-exclusion principle, because I know what's inside of A union B should be the probability of A plus the probability of B minus the probability of A intersect B. And I've got all those things. A has a probability of 0.6, and B has a probability of 0.5, and A intersect B has a probability of 0.4. So altogether, the chance that A or B or both will happen is 0.7. Okay, so A union B, I just used a formula. If I'm looking for something more involved, A intersect B complement, then maybe instead of using a formula, a Venn diagram might be a good choice. Kind of the same thing as the English and French example that we looked at previously. So I'll do the same sort of work that I did there, where I'll say I need to fill in my Venn diagram starting in the middle and working my way out. A intersect B, that probability was 0.4. And then now we'll start to work our way outside. A, that whole event is supposed to have a probability of 0.6. We already have 0.4 in there, so 0.6 minus 0.4, that's 0.2. For B, it's supposed to all add up to 0.5. I have 0.4, so I need another 0.1. These three things, 0.2, 0.4, and 0.1, they all add up to 0.7, which that confirms our answer, because remember previously we said inside of A or B or both, it should all add up to 0.7, and it certainly does, which means in our sample space, there should be 0.3 remaining to be put in the exterior. Okay, so now I'm ready to go. Now that I've filled in my Venn diagram, any question I might have, I can just refer to regions on the Venn diagram. We want A intersect B complement, so you need to be inside of A and at the same time not inside of B. So in other words, only inside of A, and those are the 0.2 that we have there. So the probability of being inside of A intersect B complement should just be 0.2. One last thing just to mention, and I'm not going to really care about odds all that much, I'm just going to mention it briefly, and that's because in everyday language, a lot of times people will use the word odds when they're referring to probability, and they're not exactly the same thing. So when we were talking about probability, it was a ratio. It was how many successes did we have out of how many things in the sample space in total. Odds are defined slightly differently. So when we're defining odds in favor of something happening, it's a ratio, but the ratio is in terms of how many success options there are to how many failure options there are. So, for example, if we're rolling a six-sided die and we're interested in the event where the roll is a 2, odds in favor the odds in favor of rolling a 2, well, there's one outcome where you're rolling a 2, and there are 5 outcomes where you're not rolling a 2. So the odds in favor are 1 to 5. The odds against is in the reverse, where you list how many options are there where the outcome doesn't happen, and then how many outcomes are there where the option does happen. So the odds against rolling a 2, there's 5 ways where you don't roll a 2, and there's 1 way where you do roll a 2, so the odds against are 5 to 1. Now, when you're talking probability, if you said probability of rolling a 2, you'd say there's probability is 1 out of 6. And that's because for probability, we're mentioning not just how many success options there are, but how many options in total. For odds, it's how many successes, how many failures, or how many failures, how many successes. So just be aware that I'm never going to be using the words odds again in this class, that if we casually use the word odds in everyday life, here in this class, we're going to be talking specifically probability. So we will never talk about odds in favor or odds against. Always it'll be the probability of an event occurring or not occurring.